talk about Turing patterns, nature's hidden blueprint. What do a zebra, a mouse embryo, and crime patterns in a major city have in common? What if I told you that it had something to do with World War II era code breaking and early computers? Still not hopeful? Well, let's start at the beginning with a man named Alan Turing. He was a pioneer in breaking the Germans' supposedly unbreakable code during World War II by designing a code breaking machine called the bomb. As a result, he's considered the father of modern computing. After World War II, he began to experiment with other fields. During this period of his life, Turing originally wanted to understand how a tiny single-celled zygote was able to develop into an entire animal. In the process of investigating this, he created a theory that could explain how patterns in nature arise based on chemical reactions. Now, you might still be wondering how this theory could be broad enough to apply to anything from fur to embryos to crime. Well, let's take a look at the theory. There are two or more morphogens, as Turing called them. One acts as an inhibitor, stopping the production of another molecule, and one an activator that does the opposite. The math that Turing applied to this theory is beautifully simple on its own. He suggested two equations, one for each morphogen, with each equation having two parts, one for diffusion and one for reaction. In the diffusion stage, the morphogens start highly concentrated in one area and spread out over the area they have available. As they diffuse, they come into contact with one another and react. This is the second part of the equation. Over time, this reaction reaches a stable equilibrium where the concentrations of the reactants are the same, but organized in a pattern of differences in chemical composition. These chemical differences can be in pigments that create patterns on the animal's skin and hair like zebra stripes or leopard spots. Here, you can see a monkey flowers patterning compared to the theoretical model. Pretty close, right? They've also been found to create a pattern of cell signals that tell certain cells to die off, while others continue to develop to create the shape of a mouse embryo's fingers and toes. In recent years, there have even been attempts to develop equations to plug into this model that would apply to inorganic patterns, such as high crime location in cities or our weather. Because the theory is so elegant, it can be customized to many applications like these merely by substituting specific equations in for the diffusion and reaction. Does it work? Well, because of the broadness of this theory, that is still up for debate. For simple examples with only two morphogens that interact and contribute to the pattern, this explanation seems to hold up very well. But in recent years, there has been more and more interest in proving Turing's hypothesis for complicated systems, which has led to discoveries such as the mouse embryo example. So, while like many things in science, there's still plenty to discover, Turing was most definitely onto something.